In this lecture, we're going to review the structure of the atom and talk about the subatomic particles and how to figure out how many protons, neutrons, and electrons there are. And we're also going to talk about some differences between the average atom and an isotope. So here's the basic structure of the atom, where the nucleus is in the middle and you have protons and neutrons in it, and electrons are in the electron cloud or on the outside. The atomic model is one example of scientific models. It's important to think of scientific models in general as being representations of any scientific concept, which helps the scientist to understand, test, and explain their ideas. So a scientific model can be a picture, like the atomic model. It could also be a computer program that's used to run trial data or to come up with different scenarios. It could also be an analogy. So a model can be anything. It does not have to be a picture. The atomic model, which we're concerned about in this chapter, is a visual representation of the atom, and we're going to talk about in our next lecture how that representation has changed as scientists discovered new things about the atom. So, the next question is, do models ever change? And the answer is obviously yes. A model can change. And that's because as new data is discovered, scientists need to revise and update their models to be consistent with the new data. Otherwise, we would still be looking at, for example, a model of the Earth as being a flat map. So now we know that the Earth is not flat, and we have the globe to represent us as a model. The subatomic particles are protons, neutrons, and electrons. So this is easy to remember because sub means under, like subway is under the street. So subatomic would be things that are under the atom or make up the atom. We have since discovered that there's more subatomic particles than protons, neutrons, and electrons. Even protons and neutrons and the tiny electron isn't the smallest piece of, isn't the smallest thing in the world. There are smaller things that you'll learn about in physics, but for chemistry, these are the smallest things we'll talk about. So as you know, the electron is located in the electron cloud, and it has a charge of -1. The proton is located in the nucleus, and it has a charge of +1. And the neutron is named that way because it is neutral, so it has no charge, and it is also in the nucleus. Unless you're going to be doing experiments involving the mass of an electron, knowing the masses are not important, but what's important to notice is that the mass of the proton and the mass of the neutron are almost identical for the 1.67 and then 1.67. And again, remember, this is a tiny, tiny fraction because that's times 10 to the -27th, so they are almost identical to each other. What is important also to notice is that the mass of the electron is much smaller than the mass of either the proton or the neutron. And you can tell this by looking at their exponents. So this is 10 to the 27th versus 10 to the 31. There's a difference of 10 to the 4th. So that's a pretty big difference in size. So in terms of counting or figuring out how many protons, neutrons, and electrons there are for every element, we need to look at a couple different things. And the most important one is probably going to be to look at the periodic table as a tool, and on the periodic table there's a couple numbers we need to know about. The first number is called the atomic number. This is the number of protons, and this is also what the characteristics that identifies what an element is. So if you look at an element and it has atomic number 3, it's going to be an element or an atom of lithium. If you see an atom and it has 6 protons or an atomic number of 6, we know that that is going to be an atom of carbon. The mass number is the total number of particles in an atom's nucleus. And the way we find that out is it is the sum of the protons plus the neutrons. So that is for any given specific atom. On the periodic table, however, they don't use mass number. They use the average atomic mass, and that is because not every atom of an element has the exact same mass number. So the average atomic mass listed on the periodic table is the weighted average of the mass numbers of all isotopes of an element. What that means is if you have 100 atoms of carbon and 50 of them are carbon 14 and 50 of them are carbon 12, then the mass is going to be somewhere in the middle, and you would say the average mass is 13. However, what if 90% of those carbon atoms were 14 and only 5% or 10% were carbon 12, then the mass would be much closer to be 14 because that represents that most of the sample has a mass of 14. That's what a weighted average means, and that is why all the masses on the periodic table are almost always a decimal. So the way we can figure this out on the periodic table is by looking at the atomic number, again, which tells us the number of protons. That also tells us the number of electrons. They are equal to each other because atoms are electrically neutral, meaning they do not have an overall positive charge or negative charge. So we know that the number of electrons, being -1 each, must be equal to the number of protons, which are +1, so that those pluses and minuses cancel each other out. Secondly, to figure out the neutrons are not charged. So we cannot assume that protons and neutrons are equal. So neutrons do not need to be equal to the number of protons. But what you can take is the mass number, or the average atomic mass listed on the periodic table, subtract that from the atomic number, and that will leave us neutrons. Because mass number is the number of protons and neutrons added together, minus atomic number, which is number of protons, and all that leaves us is the neutrons. So on the periodic table, here's where those numbers are located. This is lithium, for example. The atomic number is usually listed on the top of the atom. Sometimes it's in the center, but it's always a whole number. Then you're going to have the symbol, and sometimes the name of the element, and then you will have a number which is larger than the atomic number, and it's often a fraction. That is always going to be your average atomic mass. Again, using lithium as an example, we can figure out how many of each subatomic particle are in an average lithium atom. That means if you took the average of all the lithium isotopes and you figured out how many they each roughly have, this is what you would get. So again, we use the atomic number 3. Atomic number is the number of protons, so that tells us that each lithium atom will have 3 protons. And since atoms are neutral, that number must be equal to electrons, so it is also 3. The tricky part now is figuring out, on average, how many neutrons are there in a lithium atom. Now, you could take this number, the 6.941, and subtract it from the 3, and you would get a fraction. But we don't want to say that the atom has a, 3.941 neutrons. We want to tell us, because you can never have 0.941 of a neutron. A neutron is a whole thing. You have one or you don't. So what we need to do is we need to round the average atomic mass to get the mass number for an average atom. So we're going to round that 6.941 to 7. Now when we subtract it, we get a whole number with 4 neutrons. Now, what if we're talking about a specific isotope, or one specific atom which is maybe different than another specific atom within the same element? So an isotope means in the same place. So it means that these are 2 atoms that occupy the same place on the periodic table. So they are different atoms of the same element, and they have, because they're the same element, the same number of protons and electrons, but they have different number of neutrons. So they are represented by this symbol where you have A over Z and X. And what it says down here is A is representing the mass number, which we know is protons plus neutrons. Z represents the atomic number, which is the number of protons. And the element symbol you would fill in there with the X. Oftentimes when you are writing about or naming an isotope, the way you call it, you don't call it necessarily by its numbers. You're going to call it by its name and its mass number. For example, sodium-23 or sodium-24 are 2 isotopes of sodium, but they are both sodium atoms. Sodium-23 means the mass number is 23. So this is what it would look like in this X, Z, and A symbol, where you have the mass is 23, so we put that at the top. Sodium's atomic number is 11 always, so we don't even have to figure that out. We just look on the periodic table and know it's 11, so we fill that in. And the symbol is Na for sodium. And we refer to it by name as sodium-23. But it looks just like our model of the atom that we looked at earlier. It is not any different. All that's different is that the number of neutrons is going to be a little bit different from its brother isotope or sister isotope. And the number of neutrons is different. Otherwise, the nucleus is going to still be in the middle of the atom. The number of electrons is the same. They both have 11 electrons, because they need to balance the 11 protons. It's just going to have a different mass number, so one will be heavier than the other. And when you pick it up, it literally would be heavier. So what if we're looking at a isotope and we're looking at this AZX formula instead of the periodic table. Now how can we find out how many subatomic particle there is in this isotope? Well, we can start with the top number. Top number tells us the mass number, which again is the number of protons plus the number of neutrons. So in this case, you would have a mass number of 8, and if you subtract that from the 3 protons, that leaves you with 5 neutrons. The atomic number for lithium is always 3, and it doesn't matter whether you're talking about the average atom, a different isotope of lithium, or even an ion, the atomic number is always 3. So that means 3 protons. And in this atom we know protons and electrons are equal, so that tells us there's also 3 electrons. So this is how many subatomic particles we have. We can do some practice on looking at carbon. We could look at carbon, and when you're given this information where you're just told the element and you're not given any specific atomic numbers or mass numbers, you need to use the periodic table. In this case we're talking about a specific isotope, carbon-14, and we don't use the periodic table because we're already given the data or information about carbon to use. So if you look on the periodic table, the number at the top of carbon would tell you 6. So the number of protons is going to be 6. Now the number of protons must be equal to the number of electrons because this has to be electrically neutral, so plus and minus balance by having 6 and 6. The average atomic mass for carbon is 12.011. So we're going to round that to 12. So if there are 12 items in the nucleus, 6 of which are protons, that leaves 6 of them to be neutrons. So your average carbon atom is going to be 666. Now if we're talking about the carbon-14 isotope, that means we know the mass is going to be a little bit different, but we're still going to have this same 6 protons and 6 electrons to balance it out. But now we know specifically for this atom of this isotope, there's going to be 8 neutrons because 14 minus 6 is 8. There we go. In the next lecture, we're going to talk about how scientists discovered all of these numbers and how they discovered all of the information about the atom and where everything is located.